in the main menu of the Zoom that allows you to record.
I think it's recording now. Can you see it, by the way?
Yes, it's recording.
Okay, good. So again, Asaf Bear is me. My mail, in case you need it, asaf.per@viu.ac.il. My office is Physics 202, room 509. That's in the 5th floor. That's enough to get you how to get me. And as I said, 20% homework, 80% final exam. Lectures currently via Zoom. Likely we're going to stay via Zoom until the end of the semester. But we'll see. That is, it's not my decision. I follow the university rules. Again, I don't need to say it again. I will say it. Please open up your cameras. That's I ask it from you. Now, another thing that I ask is that you participate. I do want you to participate as much as possible. If nothing else, I will say, just have in mind phrasing by Richard Feynman. There is a correlation between how much you participate in the class and how well you're doing in the final exam. Okay, if you participate, if you ask questions, you're likely to do better in the exam. And I definitely want to encourage you. I hope I'll be able to answer all your questions. I cannot guarantee, I'll just make an effort. What I can promise is that if you ask me a question that I do not know the answer to, I will tell you I do not know and I'll go and check. I'll come back to you in the following lecture or as soon as possible with the answer. The only questions I may not answer is if you ask me to solve your problem set. Other than that, if there is something you do not understand, do not hesitate. The reason why people don't ask questions is normally because they think that everybody else understands the answer except from yourself. That is capital mistake, especially in this course. There is something you do not understand. Trust me, you are not the only one that doesn't understand. Okay, trust me on that. I see some smiles, so that means you know what I'm talking about. Okay, we're going to start. So right now what we do today is, this lecture is going to be introduction, just to give you things to think about, right? We're not really going to do too much math now, but I'm going to give you a lot of things that I want you to think. When do the story begins? When do we start? What is the starting point of all the story? It has a date. Does any of you happen to know the date?
9:05 or 9:15?
Nearly, but I'll go earlier. I'll go earlier than that.
800 something with Maxwell.
887. 87. What happened in 1887?
Michelson-Morley.
Very good. This is called the path to general relativity. (1887), Michelson and Morley. What did Michelson and Morley do?
They tried to measure the ether.
Right. What is the ether?
It's what light would propagate through.
Right.
Supposedly.
Very, very good. Right. So we can go back to 1800, 1800. That's when Thomas Young did his slit experiment and showed that light is actually a wave. And waves, as we know, propagate in matter. And if light is a wave, it has to propagate in matter, and that matter is something that was never measured and never seen before. We know, since we're seeing the light from the sun and light from the stars, that it must be everywhere, right? So they try to measure the properties of the ether. That's important because they didn't really ask whether there is an ether. It was clear to 19th century physicists that there must be an ether, because we're seeing light from the star, so it has to be. We just didn't measure it because it's too diluted. And what did they find out? Michelson and Morley?
That the speed of light doesn't change.
Yeah, right. So they find out that there is no ether, right? So speed of light is constant, right? Very good. and we call it c, right? That's constant. So what? So what's the big deal?
So how does light propagate through nothing?
No, that's not a big deal. That's not the main thing, right? It's not the nothing. It's the fact that the speed of light is constant. Namely, it is independent on our motion, essentially, right? On the motion of the Earth. So what? By the way, it's not a dialogue between myself and one student. It's an open discussion. So I want other.
So well, if you measure the speed of light and you're moving toward it or away from it, so it will remain constant. So other things need to change. Like you need a right transformation to use to calculate now everything, because Galilean transformation are no longer available.
Very good. So you just said the keyword, right? So that means that Galilean transformation, the immediate consequence of Galilean transformation is invalid. Right? What is Galilean transformation? Right? They just said that u prime is just u plus or minus v, right? You have two observers, they're moving with respect to each other at some velocity v, and they're both seeing a third object that is moving at some velocity. So one would say the velocity is u, the other said the velocity is u prime, but you can easily transform between the two observers, right? I have one observer, and there is a second observer, which is moving at velocity v, and they're watching a ball which is moving at some speed, right? So we would say that the ball moves at speed u, u, and she said it moves at u prime. Right, and this is transformation between them. Okay, so it's invalid. That is what it means. So what?
So Newton is invalid.
Exactly, and that's the thing. That's the main thing. Newtonian mechanics is invalid. That's the key. Now, Newton wrote his Principia at 200 years before that, I think 1687, right? And for 200 years, you know, Newton was long dead, right? So 200 years, every experiment that was done was in perfect agreement with Newton's theory. This was the first time, 200 years after Newton wrote his theory, right? Newtonian mechanics, long after he was dead, that somebody came up with an experiment that showed that there is something wrong with Newtonian mechanics. Something there is incomplete, it's invalid. Okay, now you all see, because Newtonian mechanics is entirely dependent on Galilean transformation. You go to the center of mass, right? You cannot go to the center of mass anymore if Galilean transformation is not valid. Now, the next step, right? So the next step, as you already said, was 1905. What happened in 1905?
Spatial relativity.
Years of miracles, right? Special relativity, SR. Special relativity. Einstein, 26 years old. What did he do? What did he really do?
To requote Feynman, he tell you how to measure the time with a watch.
He did something very simple. He just replaced Galilean transformation with a Lorentz transformation. Henrik Lorentz was working around these years. He was still alive then. So Galilean transformation was replaced by Lorentz transformation. That's basically all he did. You can actually find this paper. Of course, it's easy to find. Now,
can I ask a question?
Yeah.
What was the original purpose of the Lorentz transformation from the beginning?
That's a very good question. That is to transformation of electric and magnetic fields. That was done by Maxwell.
I see. Thank you.
Okay. So when you do a Lorentz transformation, time is involved. So you pay the price that time is no longer a conserved quantity. Namely, two different observers do not agree on the same time. That's a pretty heavy price. And of course, that's since then root deep into the culture, right? The Western culture, at least the Western culture, maybe other cultures that I'm not aware of. Now, but what did he gain? So the first and most important thing that he gained was to get a theory which is consistent with the Michelson and Morley experiment. And behind every successful theory, there is always a good experiment. So nobody could tell you anything else is a lie. You start with an experiment, and I'm telling this as a theoretical physicist. But without experimental observation, all the theories are worthless. It's math. It could be beautiful, but it's meaningless. So what did he do? First is consistent with the Michelson and Morley experiment. Great success. Other than that, it's meaningless, right? What's the second thing? The second great thing that he got? Any idea?
Is it the mass energy relation equation?
No, it did not appear in his it did not appear in his 1905 paper actually. If you read the paper, it did not see that up until very much later, a few years later. What was the second great success?
It can agree with Newton's theory?
Exactly, very good. So in the limit of when all the velocities in the problem are much smaller than the speed of light, so in the limit, then you retrieve back Newtonian theory. It would be embarrassing, after 200 years that Newton's theory was tested and validated experimentally by I don't know how many, innumerate number of experiments, then suddenly come and say, okay, you should throw it all to the garbage. It's meaningless. So no, it's not meaningless. It's actually a very, very, very good approximation of reality as we understand it. So Newton can rest in peace. He did not make a mistake. It was very good. It was actually excellent according to all the data that was known at his time. That's the best that one could do. 200 years later, there was a new data, technology improved, new experiments were done. And now we realize that Newton was actually a very good approximation, I should say, an excellent, excellent, excellent approximation. Still an approximation, but a very good one. There is a reason why you learn it in your first year. And the third point, the third great success, which somebody already kind of mentioned that already, that by the second half of the 19th century, right, most physicists were doing what? Or I don't know if most, right? Many physicists were doing what?
Electromagnetism?
Electromagnetism, exactly, right? This is when Maxwell managed to unify the experimental results of Faraday and Ampere, right, and Gauss and Coulomb into one coherent theory of electromagnetism. And as we already said, this theory of Einstein is consistent with the Maxwell's theory of electromagnetism. Right? Remember that the solution to Maxwell's equation, this is something which you learn, they obey a solution, which is a wave solution. An electromagnetic wave travels at the speed of light. Look, that's what they did. Just a brilliant idea. Took Galilean transformation, changed it to Lorentz transformation, wrote a paper, and voila. Everything falls into place.
I actually have a question.
Yeah.
Didn't he actually assume that the speed of light was constant, whatever the frame was? We derived the mass from one observer to the other one, and then ended up showing that it was a Lorentz transformation.
No, it just used, as far as I know, it just used Lorentz transformation, but this is something which is easy to check. You can just go to the 1905 paper and read it. It's not a very long paper, actually. To the best of my knowledge, that's what he was doing. He did not get a Nobel Prize for that, right? For the Nobel Committee, that was not, they were a bit hesitating. Eventually, he did get a Nobel, of course, but not for that. And I was told this story by my brother, and I went and checked. He got his Nobel Prize for the photoelectric effect. And then when he went to he didn't actually go to the Nobel ceremony, but he sent them a speech, which was all about the relativity. Because Einstein did understand better than the Nobel Committee members the importance of that. But that did not solve anything, right? That's a great success, tremendous success, amazing. But there is still two things which are not there in this theory. What are these two things?
Gravity, obviously.
One is gravity, that's true. Still, I would say open questions, right? Open questions.
Acceleration, perhaps?
Very close to that. You're very good. So one is gravity. And two is the notion of inertial frames. Let's go over that. This is something which you're supposed to know, but I don't think it's been covered thoroughly enough. Let's start with gravity. What's the problem with gravity, by the way? Why is that not included in this theory? Any suggestion?
Because gravity was instantaneous, like
very,
it was.
Exactly. Very, very good. Excellent. Who was saying that?
I am. Yes.
Yeah. Okay. Very good. Excellent. The way we understand gravity, right? The way we teach gravity, right? So there's Newton's universal law of gravity, right? It's G m1 m2 over r squared, right? This is the universals. So between every two massive bodies, there is a force which is equal to proportional to the masses, linearly proportional to the masses, and inversely proportional to the radius. So the distance between the two bodies, right? So you have two bodies, M1 and M2, and each two bodies put forces on each other. Right? This is distance r. But as you very rightfully noted, there is no notion of time here, which means that the forces are, instantaneous. They occur right away. Think of it, let's try to visualize that. So let's say that, in a galaxy far, far away, a star moves from the right to the left, right? So according to Newtonian's theory, if we only had a device which is sensitive enough, we should be able to detect it right away. Right? That's what the theory says. But of course, this is in contradiction to the Michelson-Morley experiment because nothing travels faster than the speed of light. So it should take some time until we actually know that something had happened. Right. So this is the first problem. That's why it's not consistent. The second problem is this issue of an inertial frame. What is the issue with inertial frame? I'll tell you that in a second. I'll just say that that Einstein realized these problems in 1905, and it took him several years to try to find out the solution. Eventually, of course, he did come out the solution. This is general relativity, which indeed was invented or introduced in 1915, so slightly over 100 years ago. And the solution, the surprising solution, was to find an interpretation, the geometrical interpretation to gravity, such that the existence of a mass curves space-time. So we no longer look at space-time as being flat, Euclidean or Minkowskian. But let's first say something about inertial frames. So in Newtonian mechanics, inertial frames, they are very important frames, right? They are special frames. What is an inertial frame? What is an inertial frame?
It's just a frame of reference that is not accelerating.
It's not just. I don't like the word just. What do you mean by not accelerating?
It means that, well, either the frame of reference is constant, it's not moving at all, or it's just moving at or it just moves at a constant speed. It does not change its speed for some reason.
Constant speed with respect to what? And accelerating with respect to what?
With respect to the viewer.
To the viewer? So maybe the viewer is accelerating.
I think it.
Sorry?
I think it should obey Newton's first law. I think that's why the first law was introduced to determine.
Exactly. Very good. This is an inertial frame. What makes the inertial frame unique is that in this frame, and only in this frame, Newton's first law of motion holds, right? If no net force acts on a body, it will move in a straight line at a constant velocity or will stay at the rest if initially at rest, right? This is Newton's first law. But this first law is valid only in inertial frame, right? In other frames that accelerate, we have fictitious forces, right? So Newton's first law let's write it down. If no net force acts on the body, it will move in straight line at constant velocity or will stay at rest if initially at rest. Right, this is valid only in inertial frame. Right, because otherwise there are fictitious forces. Right. So if you have a rotating frame, right, then the Newton's first law we have to add the fictitious forces. So these forces do not act because of any physical interaction between the particles, right? Just because the frame itself is not inertial. Now, similar to Newtonian mechanics, the inertial frames are particularly important in relativity. And that's because of what's known as the principle of relativity. Let me just say it down. So principle of relativity states that identical experiments carried in different inertial frames give identical results, but only in inertial frames. Identical experiments carried in different inertial frames give identical results. Okay, but let me go back to the question which we started to have a short discussion earlier. So how do you know if a frame is inertial or not? What determines whether a frame of reference is inertial?
You could test to see if Newton's law holds.
Newton law, it's a circular argument, right? Newton's law holds only in inertial frame, but how do you know if a frame is inertial or not?
Maybe relativity to the Earth.
To the Earth?
To the lab.
No. Come on, Newton was smarter than that. Newton himself, right, realized back in the time that this is the main issue with his whole theory. How do you know if a frame is inertial?
If we don't have a force that acts on the frame, yeah.
Forces do not act on the frame. Forces act on the bodies inside, right? You're looking at the bodies, you're not looking at the frame. How do you know if a frame of reference is inertial? Okay, I see that it gets confused. So as I told you, Newton himself was thinking a lot of this problem. So he had an answer. He came up with an answer which he could justify. So Newton believed in what's called absolute space. So he says that there is somewhere in space, there is some absolute reference frame. And then every frame that you choose, you can measure whether it's moving or not with respect to this absolute space. Okay. So all inertial frames would be all the frames that are at rest or moving at constant velocity relative to this absolute space frame that he believed exists. Okay, so Newton's answer, there is an absolute space. And once you set, okay, there is an absolute space, you basically set your zero frame, then every frame, and you know you can measure it relative to this space. Now, Newton actually, tried to think of a way of proving that and make a demonstration that would prove his point. So he came up with an idea based, of course, on a technology that was available to him back 300 and something years ago. And his idea was what's called the Newton's bucket experiment. So what was the bucket experiment? Right. Let's take a bucket, fill it with water, hang it from the ceiling. So initially, the water level is flat, right? That tells us that the bucket of water is at rest, right? Now we are twisting the rope. Now we twist the rope, twist the rope, and then you leave it. So what happens? The bucket starts rotating, right? Start rotating. What?
The water will start going up the sides, no?
Yeah, initially the bucket will rotate, but the water will stay flat. But then, of course, there is a friction. And when it rotates with some friction, right? Then indeed, you're right. The water will start going up the sides to make some sort of a concave shape. Now, let's assume that you're an ant. We're going to use that assumption quite often in this course. We're a small ant. And we try to figure out whether we are in a rotating frame or in an inertial frame. So the ant look at the water. Does it see the water moving with respect to it? Here, no, right? You're seeing the water. You look at the water, you know, the ant itself is rotating, of course, with the bucket. So it looks at the water. It doesn't see any motion in the water, right? But by looking at the shape of the water, it can deduce that in fact the frame is rotating, right? Or here, let's go to the first stage right here. The bucket just starts moving, right? So if the ant looks at the water, it does see the water moving with respect to it, but how can it tell whether she's moving, the ant, or the water is moving? Well, just by looking at the water level, right? She says that the water level is flat, and she sees that the water are moving with respect to it, so it can deduce. It's a very smart ant. So it can deduce that actually the hair frame is moving, but not the water. Right? So Newton used this demonstration as a proof of existence of the concept of an absolute space. Right? So it says there is a way, even if we're not sure which one is rotating, us or the water, there is a way just by looking at the shape of the water, we can deduce who's rotating and who's not. What do you say? Clever, huh?
What would be the difference between that and hanging a stone from a rope of a bus which starts its movement? We call it negative acceleration, but the fact that the stone will move shows you that the system is accelerating.
Oh, it's essentially the same thing. The issue is if you have an independent way of telling whether your lab is moving or not, whether your lab is your lab is inertial or not. This is a visualization that demonstrates a situation in which, although you are not seeing any relative motion, right here in part B, right, the ant does not identify any relative motion of hair and the water. She can still deduce that despite the lack of relative motion, they are moving. And she can deduce that by the shape of the water. So Newton, this is a way of demonstrating Newton's key argument that there is this notion of an absolute space. So once you're rotating, you are rotating with respect to this absolute space. Now, yeah.
Before we go further, I actually have a question concerning the principle of relativity.
Yeah.
I mean, your definition is in confusion with what I have, or with what I understand. Imagine that you have two observers, right? And one is moving uniformly in straight line as compared to the other one.
Yeah.
Okay? And now you have a source of light, which emits two photons with some interval delta t. This delta t will not be equal in the frame of the two observers.
Then it's not identical experiments. Because from each one's perspective, the motion of the source would be different.
Ah, okay. So this is where the identical comes in. Okay, thank you.
Okay, so Newton lived and died, and about 150 years after he died, in the middle of the 19th century, was another guy who made a huge influence on the relativity. His name is Ernst Mach. You know him from Mach number, jets and that. So he looked at this Propagate experiment, and he had a completely different interpretation. Let me quote. Newton experiments with the rotating vessel of water simply informs us that the relative rotation of the water with respect to the sides of the vessel produces no noticeable centrifugal forces, but that such forces are produced by its relative rotation with respect to the mass of the Earth and other celestial bodies. So what did Mach said? Says, hey, Newton got it all wrong. We're seeing this centrifugal force, right? But the reason why we're seeing this, we're seeing this concave shape of the water due to the centrifugal force. But hey, this is only because we have an Earth here that puts forces on the water, right? That put forces on the ceiling. Because we have some stars maybe that have also some gravitational influence. What if the entire universe was the bucket? What if our whole universe was just a bucket, and now the bucket would be rotating? There would be no Earth, no other celestial objects. And now the bucket is rotating, but that's everything that there is in the universe. Everything else is empty. Would the water level still rise?
How does the Earth and celestial objects affect the water rising? We said earlier that it happens because of friction.
Well, yeah, but why is the water here in the first place, right? Because why they're not floating in the air, right? Because they're attracted by the gravity of the Earth. Right?
Yeah.
So again, Mach hypothesis that there is some influence. So that's what Mach says, right? So Mach says essentially that there is some influence right, of the mass of the Earth and other celestial bodies. Right? On determining the inertial frame, which determine the inertial frame. Right? This is known as Mach's principle. This is Mach's principle. So again, I'm going back. So essentially, this is conceptually a very different thing than Newton, because Newton said there is this absolute space, and Mach says no. The interaction of the masses with the environment, Earth, the sun, the galaxy, whatever, right? This is what determines the inertia, right? Inertia is relative to the large scale of mass distribution of the universe, not relative to some absolute space which doesn't exist. Okay. I told you this lecture we're going to speak about ideas. So this is in contradiction to Newton's idea of an absolute space. Now, okay, so you see the conceptual difference, right? Conceptual difference. So Newton believed, right, that inertial forces arise as a result of acceleration with respect to absolute space. And Mach says that the forces are caused by acceleration with respect to the masses, right, of the celestial bodies. Now, take a step back, right? Today, Einstein took some of both. The true answer is actually quite interesting, and it takes some of both. Inertial frames are determined by the local gravitational field. So this is similar to Mach's principle. But once you're in inertial frame, you can forget about this gravitational field. The laws of motion are independent of it. In other words, the laws of special relativity will hold in every inertial frame. So there is part of Newton which is still there. Okay. Think of that. Now another thing which I think you've seen that, but it's always been hidden under the carpet. So I don't know if any of you have thought of that. The equivalence of inertial and gravitational mass. And the equivalence principle. Okay, how many of you have noted that we're actually making two uses? We make a double use of the concept of mass. We really have two different masses. Did you see that?
Gravitational and inertial.
Right. We have gravitational mass and we have inertial mass. Right? Now, this was already seen by Newton. Right? So you have the mass that appears in Newton's second law of motion, right? F equal m I inertial A. And we have another mass that appears in the law of gravity. F equal minus G M, say M, M, G, R over R squared. If you want, write this M, G, G. Now, the first one, the inertial mass, appears everywhere. Right? The second mass, I can think of it as the coupling of the body to the gravitational field. Right? You've seen Coulomb's law, right? F equal minus K Q1 Q2 over R squared. Right? What is Q here? What is Q?
The charge.
Is a charge, right? So the charge, I can think of the charge as the coupling of a particle to an electromagnetic field, right? Some particles have a positive charge, some have a negative charge, some have a zero charge. So they're not affected by any electromagnetic field. You see, so the gravitational mass actually plays the same role as the coupling of an object to a gravitational field. It does not have to be the same as the inertial mass. There is no a priori reason to assume it's the same, right? The same as the charge is not the same as the mass. Now you see that? Do you see that? They don't have to be the same, but they are the same. Experimentally, we know that they are the same, right? Now, of course, the ratio does not have to be 1. We could have mi over mg different than 1. Could be, right? This, of course, would imply different accelerations for different bodies in the gravitational field. But we happen to know experimentally that this is the case. So experimentally, mi is equal to mg, right? With modern day technology, it's better to 10 to the minus 11. This is the experimental test that we have. One of the best measures. Now you see, you can understand that, right? And why this is so crucial to it doesn't have to be like that, but it is like that. Now there are several attempts to measure these ratios. Newton himself understood that, so he tried to make some experiment measuring it. Of course, he didn't really have a good measuring devices back in the 17th century. The one that did the experiment was called Octopus, the Hungarian guy. It's called the Octopus Experiment. Now I'm going to give you already homework right now. I'm going to send you to the web, to Wikipedia or whatever, to read about Octopus's experiment. What did he do to measure that? It's a very simple experiment. It's a very, very simple experiment. Does any of you have any clue? How to carry Octopus's experiment to measure that the inertial mass is equal to the gravitational mass?
Because the Earth is rotating, there acts a force on it.
Very good. I see some people did their homework already. Very, very well. Just took from the ceiling, he hung a cord. At the end, he put some wire, and then he took 2 masses made of different materials, like M1 and M2. And here he put the mirror just to see if there is something, and then he put the light just to see if it's moving. And that's it. Just have to wait. It's different materials. Now, Octopus was Hungarian, so he carried this experiment in Budapest, which is altitude something like 45 degrees or so, 40, I don't know, this is Earth, right? So what are the forces that act on them? You just have the gravity, right? G1, G2. And then you have the fictitious forces, right? Because of the rotation of the Earth, right? F1 and F2, right? Which is easier seen from here, right? F would be pointing out here, and G would be, of course, directed to the center of Earth. Right? This is just the Earth rotation because it's not right. Yeah. So if the inertial mass was different than the gravitational mass, then the ratio F1 over F2 would be different than G1 over G2, and we'll start see a rotation. Now we're not seeing anything. All right. Now the nice thing about this experiment that you just leave it like there, right? It can go on forever. I think it is going on forever. I don't know if the original experiment is still there, but many other experiments go like that. Right? And no, it's the same. This is an experimental fact. Why, we don't know. Right? But it's pretty much similar to saying that gravity only pulls, it never pushes away, as opposed to electromagnetic field. Now, this experimental fact led Einstein to suggest what's known as the principle of equivalence. So the principle of equivalence, we have several principles in relativity. Principle of equivalence right? I'll write it down, it's crucial, right? At every point in arbitrary gravitational field, it's possible to choose a locally inertial coordinate system such that within a sufficiently small region of that point, the laws of nature take the same form as in the unaccelerated Cartesian coordinate system. At every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that in a sufficiently small region of that point, the laws of nature take the same form as in unaccelerated Cartesian coordinate.
Moti, can you please mute your microphone?
Okay, let's digest that for a second. Let's say that you're in an elevator, right? This is Earth. It's a big building. You're inside an elevator. Now the cable that holds the elevator is being cut. So the elevator is now freely falling. No worries, there is a safety device here and they're not gonna crash. Of course, you're a physicist. So the thing of interest to you while you're in the elevator, which you're freely falling, is to measure the gravity of Earth. Can you think of a way of measuring the gravity of Earth? G, can you measure it while you're freely falling?
Not really, because you'll be floating.
Exactly.
You wouldn't be feeling gravity at all.
Exactly. Not you, no any device that you can think of. Nearly. Nearly, there is actually a way, it's a second order. I'll let you think of it at home, if you can find a way. But in principle, yes, you cannot measure. Let me say it another way. We're not in class right now. Everybody's in your own home. How do you know that you're at home and you haven't been kidnapped by some aliens? And right now, you're actually inside a spaceship that is being accelerated. And the captain, which is of course Captain Keir, asks to put the engine such that the acceleration is exactly equal to g. Can you tell that without looking outside at your window? No, you cannot. That's exactly what the principle of equivalence tells you. Everywhere you have a gravitational field, right, you can always choose a locally inertial frame in this gravitational field. This is a direct consequence of the principle of equivalence, which says that you can, of Octopus Experiment, which says that every place you have gravitational mass, it can be replaced with an inertial mass. Right? So if we're all being kidnapped by some aliens and we're now floating in space at some spaceship, which is accelerating at the same acceleration as g, we have no way of telling unless we look outside of the windows. Now that really enables to determine the effect of a gravitational field. We're going to see that in a few weeks' time, I think right after Postulate. We will see how this enables us to tell the motion in any arbitrary gravitational field. This, by the way, does not help us to say, how do we get the gravitational field? To get the gravitational field, we need to go into a different regime. Essentially, the question is how a mass produces a gravitational field. And for that, we had to come up, Einstein had to come up with a different idea, and that is to identify gravity with curvature of space-time. And we're going to devote a large fraction of this course to understanding what do we mean by curvature of space-time and how do we describe it mathematically. This course, really, there is a lot of math in it. And the principle of equivalence is incorporated into this formalism by the requirement, we're going to see, that the physical equation be invariant under general coordinate transformations. And we're going to see exactly, slowly, how these things work out. But what do I mean by that? So we have to go back a long time ago to the thing which is called Romanian Geometry. Geometry. Excuse me for my handwriting, but if there's something which you don't understand in my handwriting or anything, then just let me know. I'm still trying to figure out. Well, what is geometry? You say geometry, right? But what is geometry?
It's the shape of space.
Shape of space.
And objects in it.
Well, I have a very good definition actually myself. Who is attributed to formulating it? Euclid, right? It goes down to something like 2,000 years ago, slightly more, I think, with a Greek mathematician called Euclides. Oh, no. Okay. Euclides. Follows Euclid. Now, essentially what he did is that he showed that the geometry can be deduced from a few definitions, which we call axioms, right? Or postulates. He actually had only, I think 5 or 10, I can't remember. I think 5 really. So we really had 5 axioms, right? 5, am I right? I hope I'm not mistaken here.
Yeah, it's 5.
5. So we only had five axioms, and then everything else that we call geometry followed from these axioms by simple logic, right? So, you know, between every 2 points, there is only one straight line, right? This is an axiom, right? Now, for generations of mathematicians, I think 2000 years of mathematicians tried to see if his axioms are real axioms. You know, axioms are things which you cannot prove. You just assume them, and then by logic, you prove everything else, right? Now, axioms you cannot prove, but it's a good question, you know, whether the axioms that he assumed are real axioms, or maybe if you're logical enough, by use important logic, you can deduce one of the axioms from the other, right? Now, particular interest came with Euclid's fifth postulate, which is known as the parallel postulate. So Euclid's fifth postulate states the following. Let me write it down. If a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, then the 2 straight lines if produced indefinitely meet on that side on which are the angles less than the 2 right angles. So the parallel postulates, parallel line postulate. So we have 2 straight lines. And now we take a third line. Straight line. The third line. Well, it makes the interior angles on the same side less than 2 right angles. So this will be alpha and beta. So that says that if alpha plus beta is less than 2 right angles, 180 degrees. The 2 straight lines, if produced indefinitely, will eventually meet on the same size, on that size in which there are angles less than 2 right angles. Now, as I told you, generations and generations of mathematicians throughout history try to see whether this is a real axiom, or this is something which can be logically derived from the other axioms, and they failed. The closest was exactly at the year of 1800, I think, or very close to 1800, by a mathematician called Legendre, which I think you've heard about his polynomials in quantum mechanics, right? So Legendre showed that this proved, the mathematical proof, that this theorem is in fact equivalent to another theorem which you know very well. What is that theorem? You know very well from your kindergarten times where you played with triangles.
Two parallel lines will never meet.
No, this is essentially what it says in this Euclid's theorem.
Yes.
180% angle in the triangle.
Exactly. The sum of angles.
Percent angle. Yeah.
The sum of angles in a triangle is 180 degrees. Legendre proved, it's a French guy, of course, right? He proved that these two are equivalent.
But this is an axiom, the triangle.
It is.
I don't know.
You can think of it, you know, if you can deduce from Euclid's axiom Legendre's theorem, or vice versa. So they're equivalent.
Okay.
But let me ask you a question. Is the sum of a triangle always 180 degrees?
Not necessarily.
Why not?
Because this theorem assumes that the lines of the sides of the triangle must be straight. They can be curved.
Good. The lines are straight. They're not curved. What is curved? The lines are straight. Otherwise, it's not a triangle.
To refine what Matan says, it's assumed that we know what is a straight line. It's assumed the definition of a straight line in a one manner.
A straight line is a straight line.
No, but it's assumed the straight line is only in a flat space. But if the space is curved, you won't call it. Euclid won't call it a straight line, but you can redefine straight line.
That is what I was looking for. See, some guys are very good. I want to. I'm very happy. Don't get me wrong. I'm very happy that you participate. I want to encourage other students who may feel a little bit less comfortable to participate as well. And as I said, I see that there are several people who are not with their cameras on. Please turn on your cameras. Don't need to repeat that. Because I cannot tell if you're following or not. So please turn on your cameras. There's no reason to leave it closed. Right. The lines are straight. The space does not have to be flat, as Euclid thought. And the classical example, of course, is what happens if you try to draw a triangle on the surface of Earth. So if we draw it in class, we're not in a class right now, but you can look at your floor and I draw a small triangle, it will look quite flat, right? And the space look quite flat. And if I measure the triangle, the angles, I'll end up with 180 degrees. But what if I try to make a triangle? This is the entire Earth, right? This is the equator. And this will be the North Pole. And let's say that I draw an equator triangle by drawing a line, straight line, straight from the equator to the North Pole. And then another line along the equator. Of course, this goes straight north and this goes straight east. So there's the 90 degrees here. And then from that point here, again, I'm going to the North Pole. So this is also 90 degrees. And I also have some angle here.
So this contradicts the sum of angles theorem.
It does not contradict anything. It just says that I can think of a geometry which is very similar to the original Euclid's geometry in many aspects, but it fulfills essentially all the axioms set by Euclid except for the fifth axiom. So the fifth postulate or axiom is not fulfilled, right? So the general, this is an example, right? So the general name of all these geometries is of course called non-Euclidean geometries. Not very inspirational, non-Euclidean, non-Euclidean geometries do not fulfill its postulate. They do fulfill anything else. There are geometries. The sphere is one example. You know, drawing triangles on a sphere, right? The technical name for a sphere won't surprise you. It's called a two-dimensional space with constant positive curvature. Sphere. 2D space with constant positive curvature. Now, in fact, okay. Now, there were people who studied the properties of this space. You happen to know the names? Some of you might know. There's one name which you're sure know.
Riemann?
No, his supervisor. You know, Riemann was the PhD student of somebody. No clue? Yeah, it's Gauss. In fact, we're going to say that it's mainly Gauss. It's called the geometries are followed by three guys: Gauss, Bolyai, and Lobachevsky, GBL. But it's mainly Carl Friedrich Gauss. And the question that Gauss was asking was, okay, is there a way, I'm going to say that, is there a way to know that the geometry we deal with is not flat, it's not Euclidean, without living it? I mean, you know, in other words, can we tell that the Earth is spherical and not flat? Well, some people still believe it's flat for some reason, which I failed to understand. Of course, you can simply send an astronaut or even send a satellite somewhere to space, and then you can take a picture of it. But hey, that's an easy way. Without living Earth. Can we tell? So again, remember what we are? We are simple ants, right? We're very small ants. Without living Earth, is there a way to know that the Earth is not flat? Well, we said we're ants, but some of us are smart ants. And an ant called Gauss did actually find a way. That's known as the metric. And we're going to discuss it thoroughly. How we can deduce the properties of space without getting out of it and looking from the outside, by looking at the inner properties of space. Now that may sound like, oh, you know, it's irrelevant, we can send an astronaut, but it's very relevant because, you know, we think that the universe as a whole may actually be a 3D version of a sphere. And we cannot send a satellite outside of the universe to take a picture from the outside and see how it looks like. We must somehow find a way of understanding, well, if we want to, of course, what is the actual shape of the universe without leaving the universe. And it turned out that there is a way. And we're going to discuss this way. Now, just that you get some feeling, let's say that the universe is indeed a 3D version of that, you know, of a sphere. It could be. We'll discuss that towards the end of this course. You have to wait until June, I think, it's going to be really exciting, believe me. But do you understand the meaning of that? So let's say that let's say that we have you know, we're building bigger and bigger telescopes, as you know, right? We're trying to see deeper and deeper into space, right? So we're building bigger and bigger telescopes so we can see more and more distant stars, right? What does it mean? So one day, if the universe is like that, right? So one day we could possibly build a telescope that will look and look and look, and what will we see?
See your back.
I'll see the back of my head. That's what it means. The same way as, you know, something like 500 years ago, Magellan went west and west and west and west and west, and eventually went up, returned back to the same place that he started from. Well, not he, because he died, but some of his sailors. That's what it means. And we're going to talk exactly how we actually do that and how we can actually measure that without leaving space. So yeah, so as I said, these studies go back to Gauss, Bolyai, Lobachevsky, to be fully honest. So 3 guys mainly. So he looked at the inner properties of space, how we can say something about the space, assuming that we are this little small ant that is in there. So we cannot leave the space. We cannot get out of it. And there is a big distinction between the inner properties, which is what we see from the inside, and the outer properties, right? What an astronaut will see. But remember, the astronaut will see that the Earth is round because the Earth is embedded in a 3D space. So you see the surface of the Earth as being rounded, right? But we don't want to do that. The way, as I said, the way to measure the inner properties is called a metric. Just mentioning it to you, we're going to spend half of the semester talking about that, the metric. Essentially, this is a function which gives us the shortest distance between 2 points, x and y, or, you know, with the distance along the shortest possible path. Gives the distance between 2 points along the shortest possible path. Right. On the surface of the Earth, you know, if you are forced to go along the surface of the Earth, right, we have to go through this long line. I mean, if we could dig through the Earth, the line might be shorter, but we can't do that. Right? Airplanes have to fly. Have you seen that? You know, well, not in the last year, I guess, but before that, I assume you flew. You know, they have these maps, right? Showing them. Have you ever fly to the US? That's where you see, right? Or to the North America, right? You're seeing that they have this, you know, small airplane. They have this map, right? This is the US. Somewhere, this is Europe. This is the Mediterranean. This is us, and you're seeing this route. And route always goes something like that, right? It's not going, it doesn't seem that it goes in straight line. It always goes like in a curved line, right? Why? They don't have any interest taking you, you know, sightseeing around the world. Trust me, they know.
The Great Circle Route.
What?
Great Circle Route.
What did you say?
Great Circle Route. It's the shortest. It's
right.
the shortest.
They are taking you through the shortest path, yeah. But the shortest path, you know, they are forced to be along the surface of the Earth. And the shortest paths seem to be curved. But why does it seem to be curved? Because we cannot take a surface of a ball and make it into a 2D map, although it's a 2D, right? If you try to take a surface of a ball and plot it in a, you know, straight line, you know, a page like that, you cannot. You're always going to end up with at least 1 point which you're going to miss. Normally it will be 2 points, which will be the poles, right? That's why Antarctica looks so big. It's not really that big. It just looks very big on the maps because you cannot map it. That's called mapping, right? So, you know, that's a way of stating that the metric of a sphere is not the same as the metric of a plane page, like I have here. It's not the same. I cannot map them one to one. Okay, so that in other words, it means that the inner products of a sphere are not, this is not the same as the inner products of a page. And that's what we're going to discuss again thoroughly. Now Gauss did that. He did it for 2D, he did it for 3D, and then he asked his student to generalize what he did for n dimensions. The student was Riemann. I do not know if Gauss had any clue at the time that he gave this project to his student, but Riemann did generalize things for n dimensions, including 4 dimensions, and that's exactly what Einstein used. That's called Romanian geometry. That's why it became crucial. So yeah, so we're going to do Riemannian geometry because this is the basis, this is the mathematical basis of the general theory of relativity. And this is essentially, it's the heart of non-Euclidean geometries, which we're going to do. Yeah, we're going to generalize all the concepts that you're familiar with from Euclidean geometry, you know, length, volume, etc. We're going to see how to generalize these to non-Euclidean spaces, because that's the way things are. Also, we'll talk about derivatives, directional derivatives. It's going to be a lot of fun. I told you, you have to work hard, but it's going to pay off. Trust me, it's going to pay off. So kind of closing remarks on that. So we're going to use this 2 things really, right? There are 2 questions which you're going to ask. The first question is, how do objects react to gravitational field? The equivalence principle is going to help us resolve that. So how do objects move under the influence of gravity? That's essentially the same question. The second question is, how does the existence of a mass or energy, because of course E is equal to mc squared, curves space-time such as that it acts on other bodies to pull them? That's going to lead us, this is exactly understanding the notion of curvature. How do we, what do we mean by curved space-times? How do we describe them? That's essentially going to lead us to Einstein's field equation. This is going to be the heart of this course. You'll see it. And then we're going to get solutions to Einstein's field equations. We're going to look at several solutions. Specifically, well, that depends on time. So the 2 solutions that we will definitely do is, one is the what's called Schwarz's solution. That's going to lead us to the concept of black holes. Another solution is called the FRW, Friedmann-Robertson-Walker solution. That's going to lead us to modern cosmology. That's the Big Bang and everything that follows, the expansion of the universe, dark energy, dark matter. We're going to talk about all of these. It's all going to be here. Trust me, it's worth it. It's worth waiting to the end. Pending on time, I will likely speak also about gravitational waves. I do not want to oblige because it's a little bit more technical. That's called a weak field approximation. It's really an approximation. It's taking the same equation, approximating it under certain conditions. The reason why I'm a little bit less inclined, not that it's not important, of course, it's very important, and you know about the gravitational wave detection and the Nobel Prize that people got for that. It's simply a little bit more technical, and there's a little bit of a less insight, less new insight into it. It's more solving equations in a technical way. But depending on time, there is no reason why we wouldn't do that. By the time we get there, you'll see so many equations that we might be fed up by then. But I promise you we're going to do it slowly, and I'm going to make it such that it will be accessible to everybody. Provided that you do your homework, that you come out, you ask questions, and you be prepared, and you don't kind of stay there and you know, say nothing and listen and just somehow assume that by the time you get to the exams, you'll know it. You have to be constantly on alert. So on Thursday, I'm going to start doing special relativity. I'm going to do it in a way which you haven't seen before, because I'm going to use the vectorial and tensorial notation, and I'm going to talk about what is a tensor and what is a vector in the first place. And a lot of things which you have been seeing and have been using, but you never really thought of that. I believe, I don't want to just insult you without a reason. I believe that you've seen that, but I'm not sure that you know them all the way. We will cover them starting on Thursday. So I want you, as a homework, to go back to your first year's course in modern physics or whatever, and see back what you learned there about Lorentz transformation and about special relativity. The reason why I ask you to do that is because I'm going to do the same special relativity, but I'm going to use a completely different language, which might very much confuse you. So I want you to make sure that you'll see that what I'm doing at the end ends up to be exactly the same as you learned in your first year, only done in a very different way, which we could later generalize. So you have two things to do. You have to read about Otvosh and his experiment, and you have to do some homework about special relativity. If you want, in my homepage, you can find it somewhere. There are lecture notes I did both on first year and both on that, so you can start reading it. You can start reading them, and I'll put my lecture notes online. That's it. What I have to tell you right now. Any questions?
I have a question generally about later in the course when we'll get to Einstein's field theories. Will we also learn about, say, simpler solutions? Like, for example, a solution that would show us the connection between that and Newtonian mechanics when it comes to normal-sized objects like the Earth going around the Sun?
Yeah, you'll see that. That'll be part of the derivation.
Okay.
We'll keep on the physics. This is kind of the hardest part in teaching general relativity. It's to take the right balance between physics and math. If I do too much math, you get no clue what I'm talking about. And if I do too much physics, it will just be hand waving. It's a very, very detailed balance, which I'm very much hope I won't miss. But again, it's at the end of the day, it's your responsibility. If there is something which you feel that you're lost, stop me. We have enough time. We have 14 weeks. If needed, we'll add everything, but I don't think we'll need. We have enough time. If there is something which you don't understand, stop me. This is not a course for shy people, and it's not a course for polite people. I mean, I just gave you, in this lecture, I just gave you some of a broad overview of things to think about. I think that already tells you that we're going to speak about many things here which are very interesting and requires a lot of thought. So I really mean that. So, you know, if there is something, stop me and ask me. Okay?
Thank you. Yes, thank you.
Anything else? No? Then I'll see you on. I'll see you all on Thursday. And have a good rest of the week, and do your homework and enjoy the semester. I'm sure it's going to be a lot of fun.
Thank you. Goodbye.
Thanks. Bye, sir.
Bye.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye.
Recording.